In section 4.3, we're going to talk about three-dimensional moments, 3D moments. So in 3D, moments about a point may cause bending or twisting or both. So imagine if you're standing up and somebody comes along and grabs your shoulders and then gives your body a good twist. Clearly you would experience a twisting moment and a twisting situation. If you were going to bend at the waist, you would have a bending situation, or a bending moment might cause that. If you were going to have your shoulders twisted and bend at the waist at the same time, that would feel pretty odd, but your body would experience a both twisting and bending moment at the same time. Well, that happens with three-dimensional structures all the time. We're going to talk about how and when that might happen. In order to resolve those moments, we're going to use the vector cross product method. And so the vector method should define the force as a Cartesian force vector. So we need the I, J, and K component of that force. And then we're going to look for an R vector that goes from the point that you care about, the point of interest, to any point on the line of action of the force. So it's important to understand the line of action, find that point that you care about, and draw the R vector to some place along the line of action. Then we're going to perform the cross product. Again, you have done this a little bit in 2 dimensions. You've probably done this before in other courses, but we're going to find the moment about the point is going to be equal to R cross F. We're going to set up a 3D matrix and take that determinant. And the way we do the multiply is we're going to say for the R vector, or for the I component of that, for I, we're going to say that times that minus that times that. And for the J component, we'll say it is going to be that times that minus that times that. And for the K component, we'll say it is that times that minus that times that. The only thing to keep in mind is that when you do the multiplication, the J vector is a negative right there. So these are both positive as we add them, but in the middle, the J vector will be negative. If we're looking for the magnitude of the moment, then we'll take the square root of the sum of the squares of the individual moment vectors. In other words, that will be the moment about O. This is the moment about the y-axis, and this is the moment about the z-axis. Now all moments are 3D. In 2 dimensions, we basically look at a 2-dimensional model of what really is a 3-dimensional moment. And we'll talk a little bit more about how that works. But in 3D, just imagine that if you're twisting your fingers around the z-axis, the k-axis, the moment vector will be in the z plane or in the z direction. So by using the right hand rule, we're going to say that if you twist this way, the moment vector is perpendicular to that xy plane. Now here's a picture of a tractor pulling over a tree, and what we have here is a bending moment. In other words, if I attach the tractor here, it's going to try to bend it in this direction. It's going to bend it about that axis, or that axis right there. And if we want to find out the moment vector, we'll take that point, and the moment vector will go in that direction. But that is a true bending moment only. If you get a 3-dimensional problem that looks a little more like this, it's pretty hard to see and feel the moments, or the bending versus the twisting, but most assuredly there's going to be a combination of what's going on there. And then once you define the moment vector, you can draw it. You can say that the moment vector has I, J, and K components, and what that means is it becomes the axis about which the object wants to rotate. In other words, if the moment vector looks like that, this is going to be the twist, or the pretend, or the want to be twist about that axis. So going back to our tractor then, if this is the moment vector, this is the axis about which it will try to rotate. And you can see how they've drawn the moment twist. It looks like this, going around that axis. You could actually put your fingers around that axis, and your thumb could go along. Your thumb could go along in that way. Well, let's find the moment about A of this 3-dimensional situation. So we have a traffic light that's on a pole, and it's stuck out horizontally from the pole at 12 feet. All right, and we want to find the moment about the point of rotation, and it feels to me like it will try to rotate or try to point A is where it's supported. That's a good point to try to find the moment about. In fact, our problem asks us to find the moment about point A. So we have to define our vectors and the force vectors. So the force vector is probably pretty easy, so I'm going to say that there's a weight going down. It says it's 22 pounds. Then the r vector, so the weight, is equal to negative 22 in the k direction. The r vector, there are two r vectors actually. One of them would be, maybe they're the same, but sometimes r vectors, one will be easier to use than another. But the first one might be where if I draw a line from the point that I care about up to that point, or the point where the force is applied, I'll call that R1. And the other thing, the other point could be someplace along the line of action of the force. For example, if the line of action of the force goes down this way and crosses the plane right there, this right here could be another r vector. And I'll call that R2. Now, which is easiest to use? I don't know without doing some more work which is going to be easier to use, but I'm going to choose R2. So R2, let's define what R2 is. And you can see that this length here is 12 feet. So this distance here is going to be the 12 sine of 30, and this distance over here will be the 12 cosine 30. So we can just write the r vector, 12 cos, actually it's 12 sine 30 in the I direction, and 12 cosine 30 in the j direction. Alright, now let's perform the cross product. So we know the moment about A is equal to r cross F. So set up our 3D matrix. Now I've multiplied out the r vector. Remember, the r vector has to go in the middle, so that is going to be 6. The j component is right there, and that's going to be 10.39. And there's nothing in the k. The f vector, we've decided, is 0, 0, negative 22. And now we just do the multiply and see what we get. So remember, the I component will be that times that minus that times that. So let's go ahead and write that down there. And that is the I component of the vector. The j component will be that times that minus that times that. And this is negative, and this is what a lot of students get mixed up on. That'll be 6. And the k component. The k component is that times that minus that times that. Turns out that is 0, but I'll go ahead and write it out for you. And that's k. And then we can add those together, and you can see that the moment about A is equal to negative 228.6. Let me zoom out just a little bit here so I can get it all in. Negative 228.6 plus 132.0 in the j direction. And that's the answer that we're looking for. Now, the former problem was bending only. This one is both bending and twisting, and I think you can probably see how that's working. There's some tension applied to this boom, and you can see that where the tension is trying to lift up this weight at B. but there's going to be a twist that's going to happen around here, plus a bend that's trying to go in that direction. So we're not going to distinguish too much really between bending and twisting. It's just kind of an understanding of how the world works a little bit. So let's first define our forces. What we're going to do is sum the moments about point O, or we're going to do our calculation of moment about point O and see what we can find. So let's do that. First we'll define the tension. Tension is equal to 24, and we have to look for some distances here. We know that the magnitude is 24, and it's going in this direction. So in the I direction, it looks like it's going 6. And then in the J direction, it goes back that way, and it looks like it goes back 5. Yeah, that's negative 5 from, actually I should probably do it this way. It goes 6 in the I direction, negative 5 in the J direction, and then negative 30 in the K direction. So let's go ahead and write all this out. 6I, negative 5J, negative 30K, and we have to divide that by the square root of the sum of the squares in order to find out our total answer. So T here is equal to 4.645I minus 3.871 J minus 23.23 K. Now it's important to keep enough significant digits in your calculation as you move along. So I will try to keep 4 significant digits when I do my preliminary calculations, and when you're done in expressing your answers, then 3 significant digits would be the appropriate thing. All right, let's talk about the R vector. There are 2 R vectors that could be chosen, and similar to what we did before, the R vector could go up there, or an R vector could go here. Again, this is the line of action of the force, so any place along that line of action might make some sense. I'm going to choose this one down here. I'm going to choose this R vector here. I'll call this R1. All right, how do we define R1? Well, if I look at the total length here, it looks like it goes 6 in the I direction. That's what that is. And then it goes this distance. It's kind of hard to see here. It goes this distance in the J direction. If you look how this looks, is 18 going here, then it comes backwards 5. So this looks like 13 in the J direction. So I'll put that as R. R1 is equal to 6I plus 13J. Alright, now let's go ahead and do the cross product. Alright, so I've written out the matrix for you, and you can see what we did. The I, J, and K is important to define, which we've done. I'll make sure you put the R vector in the middle row, the force vector in the third row. Now let's go ahead and do the multiplication. Okay, I've completed the multiplication here for you, and you can see how this works. Again, the I vector is that times that minus that times that, which we have. The J component is that times that minus that times that, making sure that that's a negative. The K component is that times that minus that times that, which we have here. Whoops, I forgot to put the K here. This is a K vector right there. And then multiplying them all out, you get the moment about A is equal to negative 302 in the I direction, 139 in the J direction, and 83.6 in the K. If you had chosen to use this R vector, R2, you would have got the same answer. I'm not going to do that same multiply for you, but you should try it on some easy ones and make sure that you're convinced that it doesn't matter. You would get the same result. You obviously have different numbers in the multiplication. The tension vector would be the same. The R vector would obviously be different, but when you multiply it out, you would get the same result when you get done. Well, when you have 2 forces acting at a point, like we have here, or if the 2 forces are intersecting along, if the line of action of the 2 forces intersects at a particular point, then you can take some shortcuts, and that's kind of what we're going to illustrate here. So the first way we're going to do it is find the moment about point O caused by F1. Then we're going to find the moment about O caused by F2, and then we can just add them together. Okay? So the F1, we have a force that's defined. What is our R vector? Pretty hard to find a point to the line of action other than the point where it's tied there. So if you'll count in the I direction, I have 3 in the I direction, I have 3 in the J direction, and then -2 in the K direction, and that gives me my R vector. It goes like that. Doing my cross product, I can find the moment about point O caused by this vector, by that moment, is that. If I were to do the same cross product with F2, I didn't do the cross product calculation here, I would have got this right here. And then to find the total moment, you just add them together. 200I minus 180J plus 30K. The other way to do it is find the resultant force and do one cross product. And that's what I'm going to illustrate in this next spot. So here you can find the same result if you find the resultant force. So what I did is added that force to this force, just add them together just like we've done. That's a resultant force. That's what we have here. We have the same R vector, and then we do cross product on that resultant force, and we'll end up having the same answer. So whenever you have two forces that either intersect through their line of action or they're originating from the same spot, often you can simplify things by doing just one cross product calculation. Okay, what I'd like to do now is pause the video and use your newfound skills and find a moment about point O of this force applied to this bracket. So go ahead and pause the video for a couple minutes and then start it when you're ready. Okay, so in order to do our cross product, let's find our force vector first. And the force vector is a magnitude of 120. If you do the unit vector properly, you'll find that that is your force vector. Then the R vector. There are two places which I discovered that might be good R vectors. Here, this is the line of action of the force. This one is only in the x-axis, so that actually looks like the easiest way of doing it. You might also go that way up to R2. So I've got both of them calculated here, but 5I is probably the easiest. So I'll let you look at the way I did that, and when I get the cross product, I got the moment about O is equal to 200J minus 400K. The other way would be R2, and so here is the R2 vector, 1I plus 4J plus 2K. Doing the cross product on there, you get the same moment about O, and obviously that's is the same answer, and those are just two ways of looking at that.